So, good evening. My name is Aditya Sharma. Fundamentals of Compressible Flow course being conducted by Department of Mechanical Engineering IIT Guwahati under the NPTEL program. And Okay, so there was a slight internet disruption here. So I believe I am audible.
Yes,
Somebody
sir.
can, yeah, okay, thank you. So thank you, Dipendra, for confirming. So,
Yeah.
yes, so I was here only that this is a 12-week course. Okay, so for each week, for each week's content, we will be having such live tutorial sessions. So 12 such sessions will be there. And at the end, we will have a concluding session, 13th session. Okay, and the instructor for this course will be Professor Niranjan Sahu from, again, Department of Mechanical Engineering, IIT Guwahati. And I am here doing my PhD. Okay, here at Department of Mechanical Engineering only. So in fluids and thermal specialization. All right. So I believe we can start with today's session in that case. So whenever you have question, you can just unmute yourself and ask whatever you want to ask. I'll try my best to answer. Okay, so the contents of this session are as follows. So what I have been doing, so I've been taking these sessions previously for other courses also. So for past 2 years, I've been taking such sessions. So what I've been doing is for each lecture, I briefly discuss its content, and then through questions, we try to revise that content. All right. And then if there are numericals in some lecture, so we cover that up also. Okay, so this way we do this tutorial session, right? So, and I hope you have access to the lectures from the portal. All right. So this content is from there only basically. So what topics have been covered in different lectures, right? And then few questions are there. So first I'll be discussing lecture one and then questions related to it. Very simple question. So first uh, week basically is your review of concepts of fluid mechanics and thermodynamics. So as we know, this is compressible flow, fundamentals of compressible flow. So this basic knowledge of fluid mechanics and thermodynamics will prove handy further in the course. Okay, so so first topic is your concept and definition of fluid. So here the arrangement of molecules of different matter has been discussed, and uh, which matter we categorize as fluid. So this has been discussed here, right? Then comes properties of fluids. So different types of properties are there. So there are thermodynamic properties, right? There is equation of state. So equation of state, I hope you know, right? So if some fluid is in one state or other state, right? How do we differentiate? And then there are state properties, right? Then there is kinematics. So kinematics, we know is related to velocity, displacement, acceleration, right? Then there is transport phenomena of fluids, right? So properties are related to that. Then there are other properties also, like speed of sound and bulk modulus. Okay, so these are the properties. So this has been discussed. Then there in properties we see intensive and extensive. So what is intensive and what is extensive, right? So These are basics. So what is intensive and what is extensive, right? So extensive depends on the quantity and intensive doesn't depend on quantity, like temperature is an intensive property, right? Mass is an extensive property because it depends on quantity, right? Just give me a second. All right. Then, yes, there is one important property that governs the acoustics. This is speed of sound. So this has a lot of importance as far as the compressible flows are concerned, right? So expression for speed of sound has been given in the lecture slides, right? For gases, this is gamma RT. Okay, right. So after that, there is review of fluid statics, right? So fluid statics basically one is statics, one is dynamics, right? Dynamics is when something is moving, right? That is related to dynamics. Statics means something is still, right? It is an equilibrium. So that basically is statics, right? So before uh, this statics, there is one important topic that has been discussed, that is transport properties. Okay, so in this, viscosity has been discussed, thermal conductivity has been discussed, and then diffusion coefficient has been discussed. Right, so these three has been discussed. Just give me a second. Yes, so I was getting some noise from background. So all right, so in transport properties, viscosity has been discussed, right? Then thermal conductivity and then diffusion coefficient has been discussed. So viscosity is related to your momentum transport, right? Thermal conductivity is related to your heat transport, and then diffusion coefficient is related to your mixtures, right? Based on the difference in the concentrations. So this is related to mass transport. Okay, so these properties have been discussed in lecture one, transport properties. Okay, then there is a review of fluid statics. In fluid statics, we have one important law, that is Pascal's law, right? So Pascal's law, I hope you are all well aware of Pascal's law, what it is, right? So this we have been doing from very early classes, right? Then there is classification of fluid flow. So this is important. Okay. So while we are studying fluids, so this classification becomes very important. We should be very clear of this. So what is inviscid and viscous flow? Okay. Also, these sessions will be recorded and you can get the links of these videos on your portal only. So in the portal, in the left tab, if you will see, there will be a problem solving session tab will be there. From there, you can get this chart where you'll have all the links. So I'll keep uploading those links. So these recordings I'll just put on YouTube and the link I'll give to you there only. So from there you can retrieve these videos. So classification of fluid flow. So first is viscous and inviscid, right? As the name suggests, one will have viscosity, one will not have viscosity, right? And we know the importance of viscosity, right? As far as the stresses, shear stresses are concerned. What is the role of viscosity? Then compressible and incompressible, right? So what is compressible? So generally it's a rule that 5% change in volume if we can see, right? Or density, I believe. So that fluid is called compressible, right? So speaking about liquids, they are considered generally incompressible, right? Like if you see water. So for 5% change in its density or volume, right? So for that, the pressure that you require is extremely high, right? And talking about gases, if you see air, so relatively it's easy to compress air or gases, right? So that is why the compressibility factor comes more often in gases or air. Okay. So this is about incompressible and compressible flows. Then there is steady and unsteady. Unsteady is also called as transient. Okay, so that is changing with time. So steady will not change its properties, fluid properties will not change with time, and for unsteady, it will keep on changing. Like turbulence, you see, it is unsteady flow. Okay. Then there is laminar and turbulent flow. So these two types of flows, right? So at low speeds, generally you see flow to be laminar, and at high speed or high Reynolds number, you see uh, turbulent flow. And then there are transitional zones also, where there is transition from laminar to turbulent flows. Then there is natural and forced flows. So examples also have been given in the lecture of natural flow. What is a natural flow? So boiling of water is a natural flow, right? Because of variation in density, the flow is taking place, right? Then there are forced flows, like fan, right? We are using external force to make some flow possible, right? So this is natural and forced flow. Okay. So then there are very simple questions. So this is first question. You can read this question and try to give an answer. Okay, so first question is, the fluid is defined as a substance in which, so this talks about relation between your stress and strain. So whether it is directly proportional to strain. Okay. So how is the relation? Is it that stress is proportional to strain or strain is proportional to stress? Okay. So we have seen in lecture one that for solids, stress is directly proportional to strain. Okay. For solids, stress is directly proportional to strain. But as far as fluids are concerned, stress is directly proportional to strain rate, because there is no fixed at, it does not stop at some fixed. So if some shear is taking place, so it does not stop at some fixed strain when this shear force is applied. Okay, shear stress is applied. So the rate at which this strain takes place, so this stress is directly proportional to this strain rate. Okay, so that is why in fluids, the stress is directly proportional to strain rate. So D is the correct answer to this question. So Parth had replied to this question. Then second is this. Please read this question and try to give an answer. Okay, so question number two is, the properties that bear the relation to movement of mass, momentum, and heat for a fluid are called as dash. So I have discussed this. So here if you see viscosity, so this is for mass, diffusion coefficient, this is for heat, and this is for momentum. Okay. So these three properties: viscosity, thermal conductivity, and diffusion coefficient. Okay. So B is the right answer to this question. Okay. Then third question is there. So this is related to Pascal's law. Please try to answer this. Okay. Okay, so the use of Pascal's law we see in, first of all, fluid statics. Then this is, yes, yes. So Parth has given explanation for this, that Pascal's law assumes uniform density, which isn't the case in compressible fluids. Okay. So in that case, A is the right answer to this question. Okay. Then we have next question. Oops. So I've already given this. So this is strain rate. So we have done this already. Okay. So what will be the answer to this question? No options, fill in the blank. So others should also participate. Hari Krishna and Emmanuel. So when the vapor is at saturated state, the pressure that vapor exerts on liquid surface is called as? So the answer to this question is vapor pressure. All right. So the answer is vapor pressure. Okay, so this is from your lecture number 1, and I believe slide number 13 you can see for this. The whole explanation for vapor pressure has been given there. Okay, so this is question number 5. Then you have question number 6. Yes, what will be the answer to this question? Please try to answer this question. Okay, so Path is asking me that mm, the same type of typology of questions that will come for the final examination as well. So Path, regarding final examination, so there will be questions that will be based on assignment questions. Okay, and then there will be questions that will be based on your uh, these slides. Okay, this lecture content, right? So mostly I believe so. This is the case remains this that you have questions from your assignments also. So numerical questions from assignments are also given in your final exams. And then there are also questions asked from your lectures also, right? So this is the case about your questions. I hope I was clear and I could answer your query. Okay, so I was just saying that there will be questions from, first of all, assignments. Okay, the assignments that you are being given to solve. Okay, in the portal you have been given assignments, right? So there will be questions from that also in the final exam. Okay, then there will be questions from the lectures content that is not there in the assignments. So that will also be there. But I believe mostly the uh, numericals are taken care of from your assignments, but few other numericals are there. So in your assignments, if you see some numericals you have, right? Because the main concern remains about numericals, I believe, if that is the case with you guys also. So, but the number of questions, if you see in assignments, so not all questions, numerical questions, not all questions can be, sorry, given as numerical questions. So there are few numerical questions in your lectures also. So that you can also revise, that will prove to be helpful for final exams, right? Beyond that, I don't believe there comes there come questions from outside of that, so to say. Okay. I hope I could answer your question. Or you can unmute yourself and ask if you have to. Otherwise, all right. So otherwise, I'll proceed. Okay. So in a fluid motion, if the pressure at some location is lower than the vapor pressure, bubble starts forming. This phenomenon is called as, right. So this phenomenon is called as, it is like this. So I'll give you one from a real world. I'll give you one example that I have come across. So what happens is, so let's say this, we have this fluid. Okay. So now I'll introduce two terms. Okay. But then that those terms have not been introduced to you, I believe, till now, because you have started this fundamental course on compressible flows. Okay. I personally work on compressible flows. I work with shock tubes. Okay. So if you see, so let's say this is water, okay, and some blast, okay, let's say TNT blast takes place in water. So what we have a compression wave, okay. So this gives a compression wave which travels and hits this surface. Let's say this is air, okay. So first of all, this is a compression wave, okay, but when it hits and reflects as an expansion wave. Now, expansion wave is totally opposite of your compression wave, right? Compression wave, or you say it's a pressure wave, or what is wave? Wave basically is communication, right? A signal is being communicated. A pressure signal is being communicated in the medium, right? So some blast is taking place here, so it is being communicated through. So this basically is air, right? The medium we are in is air, but I'm talking about water. So first we have this compression wave or blast wave. Okay, here we have this blast wave, and when it reflects, it gives an expansion wave, right? And then this expansion wave also causes cavitation in water. Okay, so at the surface, cavitation takes place. Okay, let's say blast is taking place here. So cavitation like this. So this is fluid. So cavitation takes place also. All because of this, you can relate this to this thing also. Okay, so this is bulk cavitation. Bulk cavitation. So this is from your one example from real world, right? Bulk cavitation. Then there is next question. So this is related to viscosity. So what happens with temperature to viscosity? What happens to liquids and what happens to gases? Okay, so what happens to viscosity when temperature increases or with temperature? What happens to viscosity for fluids, liquids, and gases? So this is question number 7. So viscosity with temperature. For liquids, the expression goes like this. Okay, so this is an exponential change, exponential decrease with temperature. Okay, for liquids. And for gases, this is okay. So in this case, if you see the graph of this, so it will decrease. Okay. In case of this, decreases. And in this case, this viscosity increases with temperature for gases. Right? So this is it. Question number 7. Right? So this was question number 7. Viscosity for liquids decreases with temperature, and for gases it increases with temperature. Right? So Sutherland's law is applicable for gases. So this basically is your Sutherland's law. So in some numericals, this proved to be useful. Okay, what happens to your viscosity with temperature for gases? This is your Sutherland's law. Right. Then there is next question. So what will be the answer to this question? So when the fluid velocity is zero, it is denoted as dash condition. So this is, yes. So Hari Krishnan has also answered. So this is hydrostatic condition. Okay, a static condition, hydrostatic condition. So this is it, I believe, about your lecture number 1. So whether this is true or false, you can try to answer. So does Pascal law apply to static fluids only, or it applies to dynamic fluids also? So Pascal's law governs the pressure distribution of a static fluid. Okay. So this is a true statement. Okay. So Pascal's law applies for static fluids only. Then we have topics of lecture 2. This is about continum. Parth is saying, sir, wouldn't we have to specify the nature of the fluid as well? It could be static but compressible, right? Right, you are right. So previously, as I was saying, that it has to be incompressible, right? So I believe that is what you mean to say. Yes, Parth?
Yes, yes.
Yes, right. So you can, I believe you can introduce yourself to me because it's already around 1 hour has passed. So a short intro, if you would guys like to give of you. So where you guys are in which course or which program you guys are doing at present, and where you guys are from. So you can unmute yourself. So I'll feel, I'll feel more comfortable. So if you can just unmute yourself one by one. Yes, Path. Yes, you can go on, first of all.
Yeah, so my name is Parth. I'm from National Science Technology in Trichy.
Tirchi.
Okay. Yeah,
So which college you said?
NIT Trichy.
NIT Tirchi.
Yeah.
Yeah, yeah,
So
okay.
I am currently pursuing my second year in uh, mechanical engineering.
Yeah,
Uh,
mechanical engineer. Okay.
yeah, it's second year. So uh, I picked this course before I started fluids.
Because?
So no, I picked this course before I started fluids. So yeah, so I'm learning fluids along the way with this course.
Okay, okay,
So
okay.
um, I picked this because I was interested in aerospace engineering.
All
So
right, all right.
I wanted to move into CFD for my uh, into my work of research. So I picked this course to learn
Yes.
more
So you
about.
want to do in future, you want to do research.
Yes,
Yeah, great,
mostly
great,
in CFD.
great.
So
You want to do CFD. That is great. You want to work on CFD. That is wonderful. So so in my research work, I have been doing experiments till now. But yes, CFD is very important. So I'm just going through all this CFD also, but my experimentation will take some time. So after that, I'll just touch upon that also. Yes, so this is related to gas water interaction through shock tubes. This basically is this.
My
So
name is Hari Krishnan
yes,
Ravichandran.
yes.
I'm currently doing my PhD with Anna University.
Oh yeah, great. So your PhD
Okay,
is coming.
I took this course because it is relevant to what I'm planning to do. It is most likely to be about hybrid rockets.
Hybrid rockets.
Yes, yeah.
Okay.
So I think this course will be useful, especially when it comes to CFD
So this
and
is
its
yeah. So your specialization is propulsion related.
propulsion. Yes, yes.
So Anna University, great.
Uh, yeah, that is about myself.
Yeah, wonderful. And where are you guys from? Where is Hari Krishnan from, and where is Parth from?
I am from
Which states?
Velur, but Chennai. I mean, I am from Velur.
Vellore, Vellore, Chennai,
Yeah,
Tamil Nadu.
Velur, Tamil Nadu. Yes, yes.
Okay, great. And where is Parth from?
sir, I'm from Kerala, but I'm studying in Trichy.
Yeah, yeah, you're studying in Trichy, that I remember. So you're from Kerala. Great. Great to know about you guys. And Hari Krishnan is in which year of his PhD?
My first year.
Oh, first year. Great.
Yes, sir.
Okay, right. Wonderful to know about you guys, right? So now before we move ahead, we'll take a short break, 5 or 10 minutes break. After that, we will see just topics of lecture number two, and then there are few numericals, two, three numericals are there. So we shall see those. And after that, we'll continue our discussion. And Path has written something in the chat box. So we'll take this after break. Yes, yes. So after this break, we'll take that. Okay. Okay, so we can continue with the session. Okay. Yes. So Parth had asked regarding my PhD thesis. So this is basically I work on shock tubes. Okay. So I don't know you know about shock tubes or not. So this will be, I believe, beyond the scope of this session because I'll need some explanation on what are shock tubes, right? And then how we are trying to use it to study the interaction of gases with water using that and the shock wave. So then about dimensionality uh, of fluid fields. So this dimensionality, as far as the this lecture 2 is concerned, or I believe it's in lecture 2. So this is regarding flow fields, like there is pressure field. Okay. So now if you see, uh, so what I understood from the lecture's content is that flow fields. So let's say you have you have an airfoil, right? So this is a symmetrical airfoil, right? In that case, if you want to study the flow over that this flow over this airfoil, right? So this two-dimensional uh, pressure field would suffice, right? But now, if you have some circulation, right? Or some vortices are there at some point, right? Or some turbulence is there. Because if you talk about turbulence, so the basic definition of turbulence is that it is, if it is turbulent, it means it is three-dimensional. Okay, the flow is three-dimensional. So I believe the professor wanted to explain this about dimensionality of fluid flows, right? So this is about your uh, so so this is about your dimensionality of fluid flows, right? So what I have gone through, so I remember this about this topic, right? Then I hope this is I could make sense. Okay. Then there is lecture number 2. So fluid as a container. So whenever we are studying fluids, so basic assumption we take that is that our fluid has a continuum. Okay. By continuum, what we mean? By continuum, we mean that if you see the fundamental structure of the fluids, right? So these are molecules, 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 right? Now, by continuum, what we mean is that a number of molecules are there. So we can take that as a single set and consider it as a continuous entity, right? And we suppose that there are no gaps. And when we are talking about the properties, right, like pressure property or the velocity property, so we can consider it as a continuous entity, right? Because when we have to do mathematics of this fluids, so we cannot uh, talk about each molecule and then try to put it into mathematics, right? So this basically is the idea behind taking fluid as a continuum and this taking as a supposition while we are trying to study fluids, right? And then how do we define a continuum? So there is this Knudsen number, right? Lecture number 2, which is Knudsen number. So what is Knudsen number? Knudsen number basically is molecular mean free path divided by characteristic linear dimension of flow field. Okay. So this basically is your Knudsen number. So molecular mean free path, I hope you know. Okay. So when we talk about gases, so they have this random motion, right? So this molecular mean free path is related to that. And then characteristic linear dimension of fluid flow basically is the fluid that we are trying to study. Okay. So its linear dimensions. So that can we say it's a continuum or can we not say that it's a continuum? Okay. So if this ratio is less than 0.01, in that case, we say that it's a continuum flow. Okay. And then there are two other flows, right? One is slip flow and free molecular flow. So for that ranges you can see from the lecture, right? Then there is Lagrangian and Eulerian description. So there are two ways in which we can describe fluids and try to study fluids. One is Lagrangian approach, one is Eulerian approach. Eulerian approach basically is related to control volume. So what we do is, so if you talk about Eulerian approach, Eulerian approach. So we say, so this flow, let's say this flow is happening somewhere. So what we do is we take one small volume, okay, and then we try to study it. We try to apply the conservation laws in it, okay. So what is coming in, what is going out, right? Through that, we are trying to study this fluid, right? This is your control volume approach. Then there is, so this basically is control volume. Then there is Lagrangian approach in which what we do, we take a fluid element, okay, and then we try to follow this fluid element. Okay, so what is happening to this fluid element? In Eulerian approach, we take a control volume. Flow is coming here, flow is going out, right? What is with, as far as this control volume is concerned, what is happening here? So this way we are trying to analyze the fluid. In Lagrangian approach, what we do, we take a fluid element and then we track this. And what is happening with this single fluid element, what is happening to this single fluid. That is basically Lagrangian approach. Okay. Then then there is Reynolds transport theorem. Okay, total derivative is there. So total derivative basically is the summation of local derivative and convective derivative. Local derivative basically, so if you take a fluid element, right? So if you're trying to track a fluid element, so with time, with respect to time, what is change in that fluid element? So one property at a time you can take, right? So what is happening to that, right? And then convective is that with respect to space. Okay, so let's say this fluid element is moving from this point to this point, right? So in terms of space, it has moved from here to here. So with space, what is it? What is the relation of this fluid? That is basically your convective term, right? So pressure fields and so different fields have been explained using this local derivative and convective derivative. Then comes body forces and surface forces. Okay, so these two types of forces are there. So when we talk about our momentum equation, okay, so when we talk about our momentum equation, so on the right hand side, you'll see there are forces, right? Which is the cause, right? And on the left hand side, you see the effect, that is velocity changes are there in the momentum equation. Okay. Now these forces are body forces and surface forces. So body forces, what are body forces? One common body force is your gravitational force. Okay. So body force means because there is body, so there is force. This basically is the meaning of body force, right? Like magnetic force, because by virtue of having a body, we are having a this force. Then there are surface forces like pressure force that these forces act on the surface. Okay, so this is one is pressure force, and then one is your shear stress. Okay, so these two forces are there, and then there are governing equations for fluid flow, right? So this is it about your lecture number 2. Okay, then moving on to question number 11. A fluid flow is considered as continuum when the Knudsen number is dash. So this is, you can try to answer this. Yes, so the answer to this question is B. Okay, less than 0.01. Okay, then there is, okay, so this is a numerical is there. So we can try to solve this. Very simple numerical. Okay. So a solid rubber ball has its volume reduced by 12% when subjected to uniform stress of 12 kilonewton per meter square. The bulk modulus for the rubber is. Let's do this. So bulk modulus is minus V dp by dV. Okay. So change in pressure or the stress that is given is 12 kilonewton per meter square, and change in volume is minus 0.12 volt. Okay. Then by 12% it has reduced, volume has reduced. So this is V into so this comes out to be okay in its units, that is Newton per meter square. So this was question number 12. Then question number 13. So the ratio of densities of oxygen and nitrogen is this. Speed of nitrogen is equal to that of oxygen. The temperature for nitrogen is given. The temperature for oxygen has to be found. So what will we be doing? This is question number 13. So this is given as this. Then so for density, I am writing this. Okay, so I have just tried to split density. Now this is given to us. What is given to us? That speed of sound in nitrogen at 25 degrees Celsius, right? So 25 degrees Celsius is 298 Kelvin. I hope this is now T temperature we need to find out. Okay, so this is 25 degrees Celsius, 273 plus 25. Okay, this should not be a problem. And A is gamma RT by M, where M is molecular weight. And as per the question, gamma Tn2 divided by Mn2. So this is there. Okay. Now from here, if you square both sides, what you get is, so gamma and R you can cancel. You get is Tn2 by Mn2 equals to TO2 divided by MO2. This is what you get. Then what we need to find, this is TO2. Okay, so we need to find out this. So this 8 by 7 into 298. Now if you calculate this will come out to be, would you like to calculate this? Somebody would like to calculate this, how much this comes out to be? So I have this answer. This is 340.57 Kelvin. Okay, so this is question number 13. So temperature we could find based on the given information that the speed of sound in nitrogen and oxygen are same. Also the densities were given to us, the density ratios, the density ratio. If any doubt in numerical, please ask. If not, then we have next Last two questions of the session. So here we need to find out enthalpy and entropy. So let's read the paragraph. So the paragraph here says that argon gas we have been given and its gas constant has been given to us and its specific heat ratio has been given to us. So this is flowing through a tube with initial pressure and density conditions as this and this. So initial pressure and density conditions are given to us. Okay. Then we need to find out the final pressure and temperature. The final pressure and temperature are given as this. Okay. Now we'll see the questions. I'll just write down what has been given to us and then solve this. So first question is changing the enthalpy for the argon is. So let's first write down for number 14 to 15. What is given to us? T1 equals to 1.4 into 10 raised to power 6 Pascal because it is mega. Okay. Density, first density is given as 15 kg per meter cube. Okay. Then gas constant is given as 208 joule per kg Kelvin. Okay. Gamma is given as 1.67. Second pressure is given as 240 kilopascal. Okay, the final pressure has been given as this, which is also into 10 raised to power 6 pascals. Okay. So in this term, in this fashion, I'm trying to write this because later in ratios, it will prove to be handy. Okay, so then second temperature is given as 380 Kelvin. Now to find enthalpy, to find change in enthalpy, because the first question asks that what is change in enthalpy. So we have this formula, okay, Cp equals to change in enthalpy by change in temperature. Okay. Now, from here, change in enthalpy we can find out. Okay, this is change in enthalpy. So this can also be written as delta H is equal to Cp delta T. Okay. Now T2 we have, but T1 we don't have. Right. And then Cp, do we have Cp? We don't have Cp. So to find Cp, what we will do? To find Cp, we will use this. Cp is equal to gamma by gamma minus 1 into R. Okay, so this is 1.67 divided by 0.67. into R, that is 208. Now, if you calculate this, this will come out to be 519 joule per kg Kelvin. Okay. Now T1 we need to find out. To find T1, what we will do, we'll use this perfect gas relation. This is 1.4 into 10 raised to power 6. Rho 1 is 15. This is 208. T1 we need to find out. So T1 is 1.46 into 10 raised to power 6 divided by 15 into 208. So if you calculate this, it will give you, so it has given me 448.71. You can just confirm if this is correct calculation or not. So in that case, delta T is T2 minus T1 is equal to 380 minus 448.71 Kelvin. So you see temperature decreased from your first uh, state to second state, final state. Okay, so this comes out to be minus 68.71 Kelvin. So hence delta delta H comes out to be Cp delta T, that is 519 into minus 68.71. So if you calculate this, this will come out to be minus 35660.49 joule per kg. Okay, so this is it about question number 14. Then question number 15 is there. So question number 15 says that change in entropy. So for change in entropy, we have this formula S2 minus S1 is equal to Cp ln T2 by T1 minus R ln P2 by P1. Cp we have already calculated in question number 14. So which is this. Okay, Cp is this. This is T2 by T1. T2 is 380. T1 is 448.71. R is 208. Ln P2 by P1. So P2 is 0.24 into 10 raised to power 6. Okay. And this is into 10 raised to power 6. So if you calculate this, this will come out to be, so I have got this for the entropy change. So this is it about question number 15. Okay. So I had this much about this session, right? So now I'll just conclude this session. Okay. So if you'll allow me to, I'll just conclude this session. So this path had one question, right? So this is about whether so this streamline or path line, what is this about? So I did not get the context of streamline or path line. So why did you ask this question?
Actually, I had a doubt regarding the flow pattern, whether is it particle tracking or a general flow through a body. It comes under Eulerian
So
and Lagrangian description.
Okay, so all right, so this is what you are saying. See, in that, so because I have not studied this, specifically, I have not studied this, but what path line basically is that a single fluid element, we track its path, right?
Yeah.
So, so that is basically that is concerned with just path, I believe. So it
Okay.
has not to do anything with the fluid property as such, properties of fluids.
The property of the atom is not taken. It's not needed,
Yeah,
right?
but we don't call it atom, I believe, because so so this is J.D. Anderson's basic aerodynamics book is there. So there, when we talk about fluid elements, so I believe this is bunch of molecules. So we don't say it as atom as such. So because when we so this continuum I said, right?
Yeah.
So I believe that will come in that description. So
Okay.
atom
Okay.
won't be right to use a terminology. It won't be the right terminology.
Okay. Okay.
Yeah, yeah.
Okay.
So
Thank you.
you were trying to relate the Lagrangian approach with path line. This you're trying
Yeah.
to
Yeah.
yeah
Yeah.
yeah yeah. Yeah, so it should be sort of. I mean, we are tracking the fluid in terms of its properties also, but in path line, we just see the path
Only the
only.
particle
And
tracking is there.
yeah, yeah. This is
Mm.
what I understand
Yes.
from my
Yes.
knowledge.
Okay.
But yeah, particularly, I have not read it that they have related path line with the Lagrangian approach. Somewhere they have written it. I have not read it. I have not
Okay.
come across. Yeah,
Okay. Thank you. Thank you.
yeah. So, all right. So I'll just conclude this session in that case. So we had three lectures in this week one's content, right? So this was basically a review of your concepts of fluids and thermodynamics. In lecture one, basically we were introduced to fluids, right? Definition of fluids and then different properties, right? So kinematic properties, thermodynamic uh, properties were there, right? And then there were some miscellaneous properties. Then one important topic was transport properties also, right? After that, there was categorization of different fluids that we did. And from there, we moved on to some very basic questions on lecture number one for our revision. Then we moved on to lecture number two, which was on basically fluids, its governing equations, right? What is a continuum? What is a Knudsen number, right? Basically equations related to fluids. And from there, we moved on to the questions that were based on, I believe, lecture number three mostly, because numericals are from uh, that. So numericals have been discussed in that. So this is about it about this particular session, right? And thanks for joining this session. And the recordings you can get in this problem solving session tab on the portal, NPTEL portal. Okay, so thank you. Next session again will be on coming Tuesday with same timing 6 to 8 p.m. So it will be for week two, right? Till then, goodbye.